Welcome back. I hope you've had a nice little break. So moving into the second session of the day, now we're going to hear first about hydrogen production in practice, and then after that we're going to have a session on direct air capture of carbon dioxide. So first, let me invite Poul Moses of Haldor Topsoe, who's a leading provider of equipment for the chemical refining industry. Poul, are you with us?
Yes, I'm with you. I'm working from home. My dog just went crazy, but you'll have to live with that.
Yeah, as always, it's a fairly new. I guess it's not new anymore, but it's a different environment compared to a few years ago having these conferences. Yes. I think it's pretty nice actually.
Yes.
So please, the floor is yours. Take it away.
Thank you. Okay, perfect. Yes, so I'm responsible for. Thank you for this opportunity to present our view on hydrogen at scale. I'm responsible for the technology development of our electrolysis technology. I will speak a little bit more broadly on the entire power to gas. Our view on the power to gas world, because it is, as we see it, quite closely linked. I should, of course, have changed the background picture here to something that was not windmills. You have to be okay with that. I will spend a few slides on telling what Topsoe is and our relation actually to the nuclear industry, which actually goes many years back. What we have always been doing and are doing at present is that we are perfecting chemistry for a better world. We were founded by Haldor Topsoe himself in the 40s, and I would say in the early stage of the company, it was very much about feeding the world, so developing technology for producing fertilizers. And then as you moved up into the 70s and 80s, it was much more about air pollution control, reducing air pollution control. And then as we come closer to present day, it was about making clean fuels. And of course, what is the major challenge today, which is also one of the cruxes of this conference, is that we also want to play, we believe we have an important role to play in electrifying the world. The move away from fossil resources to a world based on non-fossil resources requires a much closer coupling of electricity with the entire infrastructure of how we live in a modern society. And I took this slide here, included in my slide deck, which is describing what Topsoe does, but I didn't actually take it for that. I took it for the picture on the right. But I can say what Topsoe does as a company is that we do process and design and engineering. So we design chemical plants, and then we have equipment around that, and we provide catalysts for these plants. And then, of course, we have sort of a business and technology service around that. And what the next slides will be about is the product for tomorrow, which is the fact that we are also a hardware provider for electrolysis technologies. In particular, a technology called high temperature electrolysis, which is very well suited for the hard to abate sectors, and also, as we believe it, for integration with the nuclear in the future. But the picture you see on the right, that is a picture from what in Denmark was called the Atomic Commission. And you see in the spore here on the left, and then you have our company founder, Haldor Topsoe, who's now passed away, but was active in the company until 2013. He was part of this Atomic Commission in Denmark, which in the 60s was looking at what role should nuclear power play in the Danish energy system, and which led to the foundation of a national lab for nuclear research. We never have had nuclear power for power production in Denmark, but we had in this in national lab, we had research reactors, and these reactors they led to a huge amount of material research. They were foundation for that, and out of that came actually the foundational research for high temperature electrolysis, which I'm going to talk about. We have over the year had quite a number of projects related to the nuclear industry. I just want to mention, for instance, this of using nuclear to produce heat. We were involved in a project in the late 70s, early 80s called Adam and Eve, where you produce synthesis gas at the nuclear reactor, and then you transport that through pipelines and do methanation far away from the nuclear reactor which is a very exothermic reaction which produces heat. So it's a way of transferring heat from the nuclear reactor to a site far away without the losses you would have if you were transferring heat itself, but you're doing it in terms of chemical bonds. So that means that this idea of how to use nuclear outside electricity production is something that I think Haldor has thought about a lot. And actually, when I started in Topsoe 10 years ago, we have something called Topsoe Catalysis Forum, which is a sort of looking into the future for research areas that could be of huge interest. And when I started in 11, we had one of those, and we had Carl Stuch from Idaho National Lab presenting exactly the topic I'm going to talk about today, which is integration of nuclear with high temperature electrolysis. Nowadays, of course, with the energy transition, we have a lot of dialogue with various commercial actors within nuclear, trying to establish what are the possibilities and what could be done. And then we also have ongoing research projects with a couple of nuclear research centers, which I cannot disclose, but it means that it's both sort of commercial and the R&D interactions that we have. So we have some insights, but it of course doesn't make us experts on nuclear. We are experts on what we do, of course, which I'm going to describe now. So we really believe that where Topsoe can play a role and where electrolysis and hydrogen and downstream products is critical is in the hard to abate sectors. So these are sectors such as iron and steel, chemicals and petrochemicals, in shipping, aviation, cement. These are sectors that are very difficult to directly electrify. It's a little bit back to the first speak of the day, where it's analysis with the temperature that in some of these cases you need very high temperatures. In other cases, you need fuels with high energy density. If one looks at a schematic here on what needs to happen, is that you can say what Topsoe traditionally doing and what we're also doing today is that what you see on the left is feedstocks, then you have some sort of conversion technologies, and then you have the way you use them out on the right. And what we do today and have done historically is to take fossil resources, somehow convert them into various products that modern society needs, that being fuels and chemicals. And and then what is happening now is that there's a much increased need to couple both biomass and waste to these end products and electricity to these end products. And what I'll focus on today is the coupling of electricity to end products. So the key technology going from electricity to chemical products is that you need electrolysis in order to get hydrogen so that you can produce these various downstream products. And all the boxes are shown there with hexagons. These are various chemicals and fuels, which are known processes from the fossil resource conversion. But so we have long history of doing this. Of course, you need to do tweaks to the technology to optimize it for integration with electrolysis, and we've been active in this kind of activities for the last 10 years. So we have some headway on how to do this. The difference between, in my view and our view, is that between wind and solar and nuclear is that for nuclear, of course, I have a completely different way of in terms of electricity production, but it's also the fact that in nuclear there's this possibility of heat integration with the so so that is not established what the optimal solution is. It's just to say that this is something to think about and something we would like to understand much better. What we have spent a lot of time is how to do heat integration from the electrolysis and downstream with the various downstream products. So a little bit about electrolysis. So the largest efficiency losses when you go from electricity to end products, that lies in the water electrolysis process itself. That is the process with the lowest efficiencies, and this is an illustration where you can see the energy consumption on the left. That is when you go from methane to ammonia. Ammonia is just an example here, and you would see the same if it was other products, or more or less the same. But so the methane to ammonia process is extremely efficient, and it's actually you cannot beat it if you use low temperature electrolysis technology such as alkaline or PEM. You would end up using more energy, and the majority of it, as you can see here, is on the electrolyzer. The chemical synthesis loop itself doesn't really use much energy. And then if you go if you shift from alkaline electrolysis to high temperature electrolysis, which is much more energy efficient, then you end up with a 25% energy saving, which of course matters a lot, because one of the bottlenecks in the energy transition is that the development of electricity sources required to substitute fossil resources, because we get an immense amount of energy from fossil resources today. And what we have spent time on is optimizing the electrolysis together with the downstream processes to link with fluctuating wind, and it may be one of the benefits of nuclear that you do not have fluctuating production. You would actually prefer to run at stable production. But just to say that we are at a stage where you can accommodate these fluctuations you will see from renewable energy, in this case defined as wind and solar. You can accommodate that in the ammonia synthesis without a need for hydrogen storage. So this means that the solutions to integrate with varying amounts of electricity, that they are now at the we are now in the stage where we'll have a 20 megawatt plant demonstrating this in Denmark, up and running in a few years. So this means that we really spend a lot of time on this, how to transform electricity into chemical products. And this is of course where the interesting topic lies, what is possible when you have nuclear. And now I'm going to spend some time on high temperature electrolysis, because what you can do when you have high temperature electrolysis is that you can benefit from having a heat source to provide steam, and you cannot have this benefit if you do low temperature electrolysis. So you can do heat integration. So it means that you have two variables to play with when you integrate with nuclear. While if you had alkaline, if you had low temperature electrolysis, you can just use electricity. You have no use of the heat for the hydrogen generation itself. So high temperature electrolysis, for those of you who do not know, this is the crash course. So high temperature electrolysis is an electrolysis technology that uses a ceramic membrane that can conduct oxygen ions, and it can only conduct oxygen ions at high temperature. So you need to run these solutions at high temperature. So the high temperatures means for our the way we do it, it's between 700 and 800 degrees C. And that has some benefits, not only because with the higher temperature it gives you better kinetics, and it also gives you some benefits in terms of efficiency due to some thermodynamic arguments. And that is what you see here on the right. The short version of this is that you have a certain amount of the energy that has to be provided as electricity, and then because splitting water is an endothermic reaction, you also need to provide some heat, and that heat is then typically provided as the as based on the losses that you have in your electrolyzer stack. So you can run your electrolyzer at something called thermoneutral point, where you on the stack level have 100% efficiency. You of course still have losses in your plant, but on the stack level you do not waste any electricity. It all goes into your product. So this is the main reason why you have very high efficiency when you I mean 100%, that's as far as you can get, so you cannot get high efficiency than this. And then of course in choice of electrolysis technologies, you have 3 different choices essentially. You have alkaline electrolysis, which is a very mature technology. It has actually been used to build very large industrial plants producing ammonia. It has the benefit of it runs. Here you see some important parameters for electrolysis. You have on the x-axis you have the current density, so that's essentially how much product do you produce per area of your electrolyzer, and then you have the voltage here, which is a measure of efficiency. And you see that at alkaline electrolysis, these are big installations because they run at low current densities in order to not have excessive losses. Where you have PEM electrolysis, which is another kind of membrane where you have very fast response, but again you lose efficiency. While then for high temperature electrolysis, you can have high current density. Depends on what you mean by high, but you can have in terms of current densities, you lie in between alkaline and PEM, but you have high efficiency. So for these kind of applications in large-scale conversion of electricity into chemical products, efficiency will be critical. Efficiency is critical in the fossil industry, turning fossil resources into whatever product you need, and there's no reason not to believe that efficiency will also be critical in the future, where you have substituted fossil resources with electricity. Let me just have a look at the time here. Okay. So if you just want some numbers on efficiency, alkaline and PEM electrolysis have more or less the same efficiencies. They operate in different ways, but in efficiency-wise, it's more or less the same. So you have some losses. This is kilowatt hours per normal cubic meter. So you have some losses in the plant, and then you have losses in the electrolyzer itself, and then you need to pay the heat evaporation because you go from liquid water to a gaseous phase. So you need to pay that anyway. So that is added here. When you have high temperature electrolysis, you still have losses in the plant. Then you have the stack efficiency, which is this is a thermodynamic limit, and then you also need to have the evaporation of. You need to pay the heat evaporation, but in this case, you can feed. You actually do feed steam to the electrolyzer. And of course, this heat evaporation, you can provide that electricity, but it can also come from processes either in front of the electrolyzer, so that could be a nuclear plant, or from conversion processes downstream. And as I said already previously, we have spent in the last 10 years, we have done demonstrations on integration with high temperature electrolysis with synthesis of methane, methanol, ammonia, so traditional chemicals that are produced in very large numbers and are needed for our modern society. You have these benefits of heat integration when you look at these different synthesis processes. So it means when you think in terms of nuclear integration, it may not be that your product would be hydrogen. It may be that it's more beneficial to have a product which could be ammonia, or which could be a fuel or another chemical. It depends, of course, on where this nuclear plant is located and the local market. But not necessarily that you have to think in terms of hydrogen as the end product. I would say in our discussions with the various project developers and commercial entities, it's very much fuels and chemicals that are the needed end product and not hydrogen itself. So a little bit about where we are coming from. So Topsoe had a daughter company where we tried to make fuel cells based on high temperature cells. That was not a success. Many other companies tried to do the same, but essentially got outcompeted by efficiency in gas turbines and of course by wind and solar. So we took this in 13 and used it for applications in small scale chemicals where you take CO2 and you convert it into CO. This is the product for that market. The product that will be integrated with nuclear plants or with solar and wind, it will look completely different. You essentially scale this up. So each repeating unit, these boxes you see is one repeating unit that will have an output that is more or less 10 times what we have in this product here for it to make sense. This just to show that there's actually something that is materialized in the real world. I will not spend so much time on how we make CO, but I will just show you that we have done both, as I said, demonstrations where we, in this case, we do biogas upgrading and ammonia synthesis. That is what you see in these demonstration halls here, and what you see down here in the left corner. That is one of these plants that makes CO2 to CO at a customer site. So these are now at a maturity where high temperature electrolysis are used for commercial products. Of course, in a much more smaller scale than what is needed for industrial applications. So what you see here is a 20 megawatt. Well, it's a drawing of a 20 megawatt plant. What it will look like for applications in industrial applications. Of course, for integration with nuclear, you would have many repeats of these modular units. So all electrolysis is essentially based on some sort of modularity. And what we have here is a repeat unit wherein you have coupled power electronics and stacks and all these things in an efficient way. So you can, as essentially more or less the same ideas for the small modular reactors, you can manufacture these repeatable units and get benefits of the economic scale, and that is key to bringing down the cost of electrolysis. So you have to think in terms of modular units that have, of course, different utilities, and which looks, for those of you it looks like chemical industry, or it will also look like and feel like operating not exactly a nuclear plant, but the process control is what is similar for the chemical industry. And then I want to end on this slide here, because I think this is where where there's some work to be done. So you can say the high efficiency from high temperature electrolysis, it comes from two things. It comes from the fact that the stack itself is highly efficient, and then the last gains comes from the way you integrate high temperature electrolysis with the processes around. So you have this box here around the electrolysis itself, and then downstream you could have different chemical processes. You can integrate that in a clever way to increase efficiency. And the benefit you have with nuclear is that you're actually able to also integrate with upstream. So you could have, depending of course on the application of the nuclear, you could use definitely use low pressure steam. That is what we have spent a lot of time on, because that's typically what you have in chemical industry. But maybe the steam that you would have available from nuclear would be of higher grade, and you would not have value in using it for other uses. You would rather use directly in your electrolyzer. In that case, it would require some engineering to find the optimal solution. So I will essentially stop here by saying that the high temperature electrolysis has a lot of advantages which we believe fit very well with the nuclear industry and hard to abate sectors as such. Essentially, this fact that you have high efficiency and you have this benefit of integration both with downstream and upstream heat sources, which we believe makes it very suitable for integration with nuclear. So with that, I want to finish, and happy to answer any questions.
Thanks a lot, Poul. That was a fascinating presentation. So I'd like to kind of maybe split my questions in two categories. At first, just starting with a more general view on hydrogen, taking the opportunity here to have somebody like you who obviously knows the hydrogen landscape quite well, and then from there move to the specific application around high temperature and the integration of nuclear. So if we just start with the hydrogen landscape and about the progress around electrolysis, can you give us an idea how quickly that sort of development is going right now and what we can expect in terms of cost and performance of electrolysis more generally?
Yes. So I would say since 70, I mean, this area exploded in 19, I would say. There was, as for nuclear, it requires some government incentives to drive this industry, and those government incentives, they came in 19. So you had the political winds change, especially in Europe, and then later maybe 21, 22 also in the US. And this means that if you look at the landscape of electrolysis companies, you have both established players in all of these three technologies I'm looking at who are rapidly scaling up, establishing production capabilities in 500 megawatt plus sizes. We are doing that, our competitors are doing that. So you see establishment of really supply chains and production on the industrial scale. So that is the biggest change, I would say. And then there's a lot of innovation. There's 40 plus both established players, startups, things in between.
And in terms of just to get a sense of the magnitudes here, how much hydrogen globally is produced through these electrolysis processes using non-fossil electricity versus the classical sort of steam reforming from natural gas?
So essentially nothing on purpose. You're talking something like the total in 17 and still the total market is less than 200 megawatts, so super small. But that will change dramatically in the next couple of years. Then there's a hydrogen is produced as a byproduct from the chloralkaline process, and that accounts for something like 4% of global hydrogen. But that is not done on purpose. It's because you want chlorine, and then you get hydrogen. So it's moving from niche applications like actually what I showed you for the CO2 to CO application. That is where electrolysis is used for hydrogen production today, but tomorrow it will be in the industrial sector, and that is also that is what is driving this. That you need to have really the supply chains and the production that you need for industrial products.
And in terms of cost, if you compare then sort of fossil-based hydrogen with the best-in-class green hydrogen right now, where are we in terms of cost per kilogram or megajoule, whatever unit you want to use?
So of course, cost depends a lot on electricity price, and that figure I showed, where you could see the ammonia plant, where everything was the electrolyzer energy consumption. This means that cost will depend on your electricity cost. That being said, it means in some regions where you have access to very cheap electricity, you could have. I mean, then there's a forecast of what capital cost will be, and combining those two, you have forecasts saying that you will have cost parity with fossil hydrogen, gray hydrogen by end of the 20s. But of course, there's some uncertainty to that, because this is still, we have not seen any of these large industrial projects. They are running, but they're not physically up and running yet.
So let me just well a little bit deeper there. So if you say cost parity by say 2030, can you tell us what kind of electricity price are you looking at then, and how much would then the remaining cost have to come down in order to meet that cost parity requirement? Are we looking at prices like 20 megawatt hours per, or 20 euros per megawatt hour, or like we've seen last year we had 200? It makes a big difference, of course.
Yeah. Yes. I'm just finding a graph that is good for discussing this. But I would say you need to be below 20 megawatts. A good figure is this one. This is the simplest analysis. You can find much more deep analysis in various reports, of course, but I'm a physicist of training, so you make the simplest model possible. And this is just taking, this is the minimum you will have to pay for your hydrogen. So you have hydrogen cost on the y-axis and then your electricity cost on the x-axis. And the only thing you pay for here is electricity. So this is essentially assuming that everything else is for free. So you cannot make it cheaper than this. And then you can see if you, for instance, have present day alkaline, that would be 5 kilowatt hours per normal cubic meter, so the blue line. And then hydrogen costs from methane. This is actually the hydrogen price, but it's between $1 and $2 per kilogram, and you need to be below something like 0.03. So that is what is that? 3.5 cents US dollars. We can convert that to euros if you want, but it's more or less the same in euros, of course. So it means that and that is would be the hydrogen cost in places where hydrogen is expensive, for instance in Europe. But if you're in the Middle East, then your hydrogen cost is I mean, that's the lower line here, maybe even lower. So then your hydrogen cost needs to be below 20 euros per megawatt hour. So really, really cheap electricity. And this is in this simple analysis, of course, this is harder to do if your capacity factors of your electricity sources is let's say you only have solar, so your capacity factor is maybe 1/7. Then your capital cost, which needs to be added to this, needs to be even lower. So for those of and capital cost is approximately adding 25% to these curves.
So did I get you correctly that these graphs, what we're looking at here is that if you assume that the electrolysis equipment and that is basically free,
yes.
Then okay, so you'd be very hard pressed to get these numbers without a quite significant cost reductions in the electrolysis equipment itself, right?
Yes. So if you take sort of cost predictions in various reports, then you approximately have to add 25% to pay for the capital cost. And it gets a little worse if you are down in low electricity price, of course, but as a rule of thumb. And this is just a good analysis if when you see announcements that people can reach extremely low hydrogen prices. It's good to look at this to say if it has anything to. I mean, if you need to break thermodynamic laws, I mean, then it's tricky. So the thermodynamic law is more or less the lower line here. That's the minimum heat you have to pay. Sorry, minimum energy you have to pay is 3 kilowatt hours per normal cubic meter. So you cannot get any better than that. And nothing of
Yeah, the thermodynamic law is a hard one to break, I suppose.
Yes.
Yeah, so it's
yes.
So and where are we right now in this graph in terms of the lowest price we can look at?
So okay, that depends a lot on where you are are you asking where we are on the y-axis? So on the y-axis today, you're typically at cost. I mean, you can have, because you have these regulatory frameworks that drives these first of kind industrial projects. You typically see end product, so ammonia cost or methanol or the fuels you make that are 2 to 3 times as costly as the fossil products.
Okay.
And what has happened, I would say, what has happened over the last 3-4 years is that there's now there's these framework coming, which means that you do not directly, in the beginning, of course, have to compete with fossil resources, but you have to compete with the other ways of making it in a renewable way. And that makes you can say you're competing against other green solutions. You're not competing directly because of subsidies and regulatory frameworks. You're not competing directly with the fossil resources. So that is what started in 2019 as an accelerated sense. But of course, this only happens because we and our competitors have to deliver on getting close to or get to cost parity within the next 10 years. So Yeah.
So thanks. That's a great overview actually, and it just I guess it gives me a sense of the scale of the challenge here. But of course, this graph doesn't really include any particular climate targets or CO2 prices and whatnot. Yeah.
No.
So I guess you can maybe portray a slightly more optimistic picture if you include those aspects as well.
Yes.
But then moving on then to the issue of high temperature electrolysis that you talked about. You mentioned quite a few benefits, including the higher efficiency and so forth. But why it's not? It seems obvious. Why is this not happening then?
Yeah. So for two reasons, it's the least mature technology. So there was a lot of both R&D activities and also commercial activities in applying these solutions for fuel cells from 2000 to the next 10 years. So the technology matured in that area, but it was just 4 or 5 years ago, it was impossible to make a business case for making hydrogen. So that's why we focused on the CO2 to CO, where you actually can have a competitive solution on commercial terms. So the short answer to your question is that hydrogen electrolysis is lower on the development curve, and what is needed to bring it to be relevant for industrial applications is to produce it in industrial plants, and that is what we are doing for hydrogen electrolysis, and also some of our competitors are doing. So and that will bring down the cost to a level where those assumptions I just talked about on the previous slide actually make sense. So your capital cost do not dominate your levelized cost of hydrogen.
And do you know are specific initiatives to do high temperature electrolysis connected to nuclear plants today anywhere in the world?
Yes, there are. I guess our next speaker can talk about that, but Idaho National Lab have activities publicly known, and I'm sure there's also activities in China connected to their nuclear research.
And would it be possible to sort of add this on to an existing nuclear plant, or would this be require design from a greenfield sort of investment? You have to include in the original design, or can you retrofit it, so to speak, to an existing plant?
Okay, so now there are probably people in the audience who are more expert than me, but of course you can take electricity from a nuclear plant and do it, but then you're not really integrating. You're just but if you really had to integrate it, then I think there are both regulations around nuclear plants and standards that needs to change for you to be allowed to export steam, for instance, if that make any sense for existing nuclear plants, because they are quite optimized, right? They are optimized for producing typically electricity. This means that all the steam is used for producing electricity, and that you don't have really excess steam, and if you have it, you may not even be allowed to use it. So there will be some regulatory work to do this, but technically, of course, you could do it.
So we got a question in the chat also relating to this issue of lifetimes expectancy of different technologies, and how could you handle that? Typical sort of electrolyzer has got a much shorter lifetime than the typical nuclear plant, or even other means of power production. So how does that play into this equation?
Yes, so you can say in terms of lifetime, the balance of plant of an electrolyzer plant has 20 plus years of lifetime. What has less lifetime is the stack itself. Alkaline stack has the longest lifetime. They have demonstrated in industrial settings 10 plus years of lifetime. At that point, you want to exchange them because efficiency goes down. PEM is lower than 10 years. SOEC is lower than 10 years. So a lot of our solution is to make sure that we have a solid scheme for how to do stack replacement and the service around it. And because SOEC is the least mature technology, that is also what we take on as part of our business model, that we provide this service and ensure, depending a little bit on the contract, of course, ensure that the customer gets what they need, typically some fuel or some chemical. That is built into the business model of the electrolysis companies, how to do the stack exchange.
Thank you so much, Poul Georg Moses of Haldor Topsoe. Great having you here. Thanks for taking the time to join us, and all the best of luck in the future. Yeah.
Thank you.
Thank you very much.